Okay, in this video we're going to continue our look at different types of vector products. In the last video we talked about scalar multiplication, which was a scalar times a vector, and we got a vector. In this type of product we're going to multiply two vectors times each other. These two vectors need to be the same dimension, and we're going to get a scalar for an answer. This is called the dot product, or sometimes called the inner product. Occasionally you'll even see it referred to as a scalar product because the answer is a scalar, but I prefer not to use that particular word because it might get confused with scalar times vector multiplication, which I call scalar multiplication. So this is or scalar multiplication or scalar product or scalar multiple. This is going to be dot product or inner product. So the dot product or inner product, let's take a look at this, and we'll start by looking over here at the algebraic definition. And the algebraic definition is if we let u be a vector u1, u2 up to un, and v is a vector v1 up to vn, we define the dot product here of u and v to be vectors u and b to be this dot product, and it's written with a little dot. We call it a dot product partially because of the symbol we use for it, which is the raised dot multiplication symbol. And so that is, you just take u1 times v1 plus u2 times v2 plus u3 times v3 all the way up to un times vn. So we're just multiplying the corresponding components and then adding all those together, and notice that this gives us a scalar. Okay, so let's put this into effect over here for an example. So over here in this example, this is dynamic. If you open the sketch, you can change these numbers, but right now I have the vector 3, 2, and we're going to dot that with the vector negative 1, 5. So you just multiply the 3 times the negative 1 and the 2 times the 5. So that's negative 3 plus 10 is 7, and so 7 is the dot product. So a pretty simple way of computing an answer there. So that finding the dot product, if it's in component form, is pretty simple. Now the geometric interpretation is going to take a little bit for me to explain this to you. So bear with me here a minute. So let's look at this geometrically by placing the vectors at the origin for their initial point. So the origin is point A, and it's going to be the initial point for vector u and v, and these are drawn correctly based on these particular numbers at the moment. And I'm going to complete the triangle by drawing the other side and let its length be called d. Okay, so now let's look at this and finish labeling initial point A, final point B for vector u, and then vector v goes A to C, then d is the distance from B to C. By the way, how long is u? Well, I use the Pythagorean theorem, or the norm formula, and that's 3 square plus 2 square and then square root. So 3 square is 9, 2 square is 4, 9 plus 4 is 13, so square root of 13 is u, is the norm of u. That's the length of the blue line segment. How long is the green one? Well, that's the norm of v. At the moment, that is negative 1 square plus 5 square and then square root. So that's 1 plus 25 is 26. So that's the square root of 26 for the green one. Okay? Alright, we'll come back to that in a minute. We want to find the length of this other side. Well, notice if we call this angle between them theta, notice that we have these two sides, and we could find theta if we knew the other side. In fact, we could find the other side because if this is at the origin, then this point B is the point 3, 2, u1, u2, and the point C is the point v1, v2. In other words, negative 1, 5 are the coordinates of C, and then the coordinate of B there is 3, 2. Alright, so just use the distance formula to compute the distance from point B to point C, and then let's work that out. We can also use the same time use the law of cosine. So the law of cosine says d squared equals the norm of u squared plus the norm of v squared minus 2 times the norm of u times the norm of v times the cosine of that angle theta between them. So remember, theta is the angle between the two if you put them tail to tail. Okay? So here we have d squared is norm of u squared plus norm of v squared minus 2 norm of u norm of v cosine of angle theta. That's the law of cosines applied to that triangle. D is v1 minus u1 square plus v2 minus u2 square. That's the square of the distance by the distance formula. In other words, really just the Pythagorean theorem. And similarly, the norm of u square is u1 square plus u2 square, and the norm of v is v1 square plus v2 square. So that's the definition of the norm. And then we've squared it. So we've kind of the squares here, here, and here have canceled out those square roots that we would normally have there. And then I'm just going to leave this other part from the law of cosines, negative 2 norm of u norm of v cosine theta. Leave that alone for the moment. I can drop the parentheses on the right side, but I'm going to FOIL out on the left, use the distributive property to expand this. So this is first term square, last term square, both positive. Multiply and double for the middle. That's the shortcut for squaring a binomial. And so that's v1 squared minus 2u1 v1 plus u1 squared. And similarly, you square this one, you get v2 squared minus 2u2 v2 plus u2 squared. So that was the distributive property. Now what I want you to notice is all of these terms right here with squares are going to cancel out. See that u1 square cancels with that u1 square. That u2 square cancels with this u2 square. This v1 square cancels over here with the first term. And the v2 square cancels with this by adding the opposite of these four terms to both sides. So that cleans it up a bit. Now we're down to here. And if we notice, I see negative 2's everywhere. So if I divide everything by negative 2, I get u1 v1 plus u2 v2. Whoops, no square anymore. Shouldn't be a square there. Let's see if we can get rid of that. And those square here. There we go. Alright, so now we have on the left side u1 v1 plus u2 v2 equals, on the right side, norm of u norm of v cosine theta. Well, that left side is exactly the definition of u vector u dot vector v. So we have now an alternative formula of the dot product. The dot product we got by components was u1 v1 plus u2 v2 in 2 dimensions. But in this way we see that the dot product is the norm of u times norm of v times the cosine of the angle in between. And we'll say that this is also true in multidimensional things as well. So this allows us to solve for that angle that's between the two vectors. Thinking of it as the smallest positive angle, that's what an arc cosine returns. So theta is well, first of all, divide both sides by these two norms, so that gets the dot product over the two norms. And then that's cosine of theta, so to solve for theta we take an inverse cosine or arc cosine. And so theta is arc cosine of u dot v over norm of u norm of v. So look at what we've done so far. We've been able to define algebraically up here the dot product in terms of components. Just multiply the corresponding components and add them up. In two vectors, you're only going to, two-dimensional vectors, you'll just have the first two. Three-dimensional vectors, you'll have 3 terms. But we can define it for any number of any dimension there. And then we have this alternative form right here that we came up with for the dot product, where the dot product is the product of the two norms times the cosine of the angle in between. And that allows us to solve for the angle in between if we know the component form of the two vectors. This, of course, is a way we can find the dot product if we know the magnitude and direction of the two vectors, because if we know the two magnitudes, we know these two things. Those are the two magnitudes. And that's if we know the two direction angles for u and v. With a little bit of look at it and thinking about it, we should be able to figure out what the angle between the two is. And so we could do that Plug that in this formula right here, and then we have the dot product that way. Now let me show you another thing that we can do. We're going to resolve the vector u into two components, one in the direction of v, or its opposite, and one perpendicular to v. When we deal with vectors, we often use the word orthogonal where we're talking about perpendicular. And sometimes we talk about a normal vector as one that's perpendicular. So when you're dealing with vectors, the word normal, orthogonal, and perpendicular are really all the same thing. So let's take a look up here at our picture and see what we're talking about. So what we're going to do, remember how you could take u and you could break it down into a vector going along the x-axis and one going parallel to the y-axis. Well, we're going to do the same thing, but project it now not down perpendicular to the x-axis, but rather perpendicular to this green vector v. And so we bring down a perpendicular there to the line containing v, and this gives us two components. One is along v, that's a, and it could possibly be pointing the opposite direction of v, or the same direction, but it'll be along the line containing v. And then you got this one that's orthogonal or perpendicular to that. So we have a perpendicular component and a parallel component. How big is A? Well, let's look at that a minute. Let's see if we can get down here and look up there. I can't look up there at the same time. Okay, we'll come down here and then go back up. So remember, the cosine of theta is A over the norm of u. Let's look at this. So the brown length over the blue length is the cosine of this angle theta. So cosine of theta is A, which is this length, over the norm of u, which is the blue length. Okay, and so that's where we get to that. Solving for A is the norm of u times cosine of angle theta. But wait a minute, cosine of angle theta we just saw was what's in this fraction right here, the dot product over the two norms, and the norms of u's cancel, and so this simplifies to the size of A is the dot product divided by the size of v. Now notice that v over the norm of v, this part right here, is just a unit vector in the direction of v. In other words, a vector of length 1 in the direction of v. If you want to take a vector and shrink it or expand it, whatever is needed, to get a unit vector, all you have to do is divide it by its own norm. And you will get a vector that's in the same direction as the one you started with, but has only length 1. So if you think about this, this is the same as taking u and dotting it with a unit vector in the direction of v. So here's the bottom line right here, is that you can think of, right here, you can think of the dot product of u with a unit vector in the direction of v is the component of u in the direction of v, which is a scalar length, which we're calling a. If we want to now turn that into a vector a in the direction there, okay, that's the vector projection of u in the direction of v. It's a vector of length a in the direction of v, so it's a times v over norm of v. And if you put this formula back in place of a, that's the dot product over the norm of v squared times vector v. Alright, let's see that in place in our example up here. So if we want to find this component here, this is going to be u dot v over the norm of v. Well, u dot v was 7. The norm of v was the square root of 26. So this length is 7 times the square root of 26. And so if we were to take that and make this vector v, it's going to have two components. Its length is 7 over square root of 26, or about 1.37281, and that makes the components approximately negative 0.26923, comma, positive 1.34615, and that would be the vector here in xy component form. This is often useful because we can let's say we're trying to push something up this hill, and we're putting a vector in this version, in this direction. This part of the vector has the tendency to make it go up the hill. This part of the vector has a tendency to make it leave the hill. Okay? More often you'll have this vector in the other direction when you're going up a hill. So you have a vector that's going down, but like if you're pushing on the, let's say you've got a push lawnmower, you're pushing on the handle, okay, the force is going down the handle. Part of that force is going perpendicular to the ground, and that's just pushing it down on the ground, whereas the other component is the part that's pushing it forward. And this would be like finding the part that's pushing it forward. So that's sometimes useful to find, and that does give us a geometric interpretation. So let's review here. We have a scalar multiplication, which is a scalar times a vector is a vector. This multiplication is the dot product, sometimes called the inner product, which is a vector times a vector, which equals a scalar. The algebraic definition is pretty straightforward. You just take the product of the x components plus the product of the y components and add them together if it's 2 dimensions. In 3 dimensions, you got product of the x components plus product of the y components plus product of the z, or in n dimensions, take the product of each corresponding component and then add them up. So pretty straightforward. Then the geometric interpretation, when it was all said and done, we had a couple ways of looking at it. One is we have this alternative formula. If you basically got magnitude and direction, you can find the dot product this way. It's the magnitude of u times the magnitude of v times the cosine of the angle in between. That allows us to solve for the angle in between the two vectors if we know the component forms. So that's the angle in between theta is the arc cosine or inverse cosine of the dot product divided by both of the two norms. Finally, we said that we could think of this in terms of components, and the dot product of the vector u with a unit vector in the direction of v is the component of u in the direction of v, which is a scalar length. Okay? And if we just do the dot product of u and v, you get a multiple of that length by the norm of v. So when we divide out by the norm of v, then we have the length of that projection. Okay? And there's a vector. What do? We just take this u dot v, divide by the norm of v squared, and multiply that by v, and that will give you a vector, this vector here, the components of this vector A, in the direction of v. And so that tells us something about the dot product. So the dot product tells us something about this component in the direction of v, and it also gives us a nice little easy way to find a number, which actually turns out to be a scalar, okay, which is the product of the two. So there is the dot product.